Hello, everyone. Today we're going to be covering the study that talks about the improving distributional similarity with lessons learned from word embeddings. And first, we're going to cover, I'll briefly talk about the agenda. So we'll talk about the introduction, give a brief background on the methods and the different hyperparameter techniques, and then we'll go over the results and the discussion.
Back when this paper was published, Chien suggests that neural network-inspired word embedding models outperform traditional count-based distributional models on word similarity and analogy detection tasks. However, the author was interested in a research of what actually makes the modern word embedding better. Therefore, the author conducted several experiments to test if hyperparameter tuning techniques or the algorithm difference that makes word embedding model outperform traditional ones. In this paper, the author refers to positive pointwise mutual information matrix and singular vector decomposition factorization as count-based representations, skip grams with negative sampling and global factors as word embedding models. I will introduce each of the models in the following slides. So the first one, positive pointwise mutual information matrix. It is one of the traditional count-based distributional models that construct a high-dimensional sparse matrix. And each row represents a word, and each column represents a potential context. The value of each matrix cells represents the association between the corresponding word and context. And you can see the formula here. And the author also suggests that having the positive value in each matrix cell will be better performance. So they use the formula on the bottom. The next, singular factor decomposition factorizations. This is also one of the traditional count-based distributional models. The difference is that having a dense low-dimensional factors will have a faster efficiency and better generalization. The method is used to find optimal rank D factorization with respect to the L2 loss and keep only top D elements of the diagonal matrix of the eigenvalues. And you can also see the formula here. Then the word representation and context representation will also be updated. Next, let's have a quick review of word embeddings. So it is used to represent words as numerical factors, and it also captures the semantic and syntactic meanings of words. And the most important part is that it can also be learned from unlabeled text using unsupervised machine learning algorithms. So work-to-fact is just another algorithm that creates word embeddings. With this algorithm, each word will have two factors. One word factor captures the semantic and syntactic meanings, and the second context factor is used to predict the probability of a word occurring in a particular context. So with that, the first algorithm they use is skip grams with negative sampling. It is one of the models in work-to-fact, and with this algorithm, similar words will have similar factor representations. They also use negative sampling, which improves training efficiency. So the network only updates the weights that lead to positive and negative samples instead of whole network. The other word embedding method is global factors. It uses a co-occurrence matrix, which represents the frequency of word co-occurrences in a corpus. And you can see the formula here. The bias term, the B, and the B bias terms give it an extra degree of freedom over SVD and SGNS. It used a weighted least squares regression to fit word factors to a co-occurrence matrix, which giving more weight to frequent pairs.
So next, we're going to be covering the hyperparameter techniques that are used in this experiment. And so when we're talking about the hyperparameters, we're more specifically talking about modifications and system design changes that we're making to these algorithms. And it was found that using hyperparameter tuning actually significantly improved model performance for each task. And so there's three different types of hyperparameter tuning. There's pre-processing, association metric hyperparameters, and then post-processing hyperparameters. So pre-processing affects the algorithm's input data. The association metric hyperparameters defines how word context interactions are calculated, and then post-processing modifies the resulting word vectors. So first, I'm going to be covering the pre-processing hyperparameters. The first one being the dynamic context window. So rather than a standard context window where the window size is fixed, dynamic one essentially will be a changing window size. And this follows the intuition that the context closer to the target are more important, and the context words can be weighted according to their distance from the single focus word. And this is implemented in primarily both Glove and Word2Vec, as well as the other count-based methods that are covered in this paper. Specifically for Glove, it uses a harmonic function. An example would be that a context word 3 tokens away will be counted as a 1/3 of an occurrence. And in Word2Vec, the weights are focused by distance and the window size. For example, a size 5 window will weigh its context by 1/5, 2/5, 3/5, etc. And this method was found to be faster in training time. And the next one I'll be talking about is subsampling. So the formal definition of this is we're trying to randomly remove words that are more frequent using some threshold T and using that to calculate a probability P at which we're going to be removing the words. And so T in this experiment was 10 to the -5. And then a sub method of the subsampling was dirty subsampling, which involves removing tokens before the corpus is processed into word context pairs, and this in turn affects the window size. And then another method that was used for the pre-processing was deleting rare words. This is pretty self-explanatory. It removes rare tokens from the corpus before creating context windows. However, this method was not formally tested in the paper, as in preliminary experiments, this showed a very small difference in performance. Next, we'll be talking about association matrix hyperparameters. The first one that we'll cover is shifted PMI. So as Peter talked about, we have the pointwise matrix. But specifically for shifted PMI, we're going to be changing that PMI value with a hyperparameter K. So SGNet has a natural hyperparameter K, and this K value has two purposes. One of them is that it's used to better estimate distribution of negative examples. And the other is to be acting as a prior on the probability of observing a positive example versus a negative example. And so the K in this experiment is mostly focusing, or the shifted PPMI is focusing on the K for the second reason. And in this experiment, 3 values of K were used, 1, 5, and 15.
Then we have context distribution smoothing. In Word2Vec, negative examples are sampled according to a smooth unigram distribution, where all contexts count are raised to the power of alpha. And context distribution smoothing alleviates PMI's bias towards rare words, and does so by enlarging the probability of sampling a rare context, since the probability after taking into the power of alpha, it's greater than the original one. And the PMI of W and C, the context cell, word and context cell is then reduced for any W co-occurring with the rare context C. And this study experimented with 2 values of alpha, 1 being unsmoothed and 0.7 being smoothed. The following we have post-processing hyperparameters. First, we have adding context vectors. And adding context vectors effectively adds first-order similarity terms to the second-order similarity function. And so take an easy vocabulary example with cat. So for the vector of cat will be the combination of word vector of cat with the context vector of cat. And the second order terms measure the extent to which the 2 words are replaceable. And the first order terms measure the tendency of one word to appear in the context of the other. The similarity the similarity measures are calculated with the equation below, and words are considered similar if they tend to appear in similar contexts, or in other words, they tend to appear in the context of each other. And this technique is not applicable for PPMI, but all other threes. Then we have eigenvalue weighting. In SVD-based factorization, the word and context matrices have very different properties. The context matrix is orthogonal and the word matrix is not. So factorization is needed to make them more symmetric. And in addition to the symmetric approach, the variant added a parameter P to control the eigenvalue matrices, just as below. And this study suggests that the weighted eigenvalue matrices have significant effect on the performance of the models. And this study experimented with three values of P, with P equals 0 and P equals 0.5 being the symmetric variant of SVD, and P equals 1 being the traditional factorization. And this technique is only applicable with SVD method. Vector normalization. The study actually experimented with 4 different normalization, and the 4 of them being none, row normalization, and column, and then both row and columns. And they found that the row normalization is consistently superior to the other 3. So that's what they decide to stick with for the rest of their experience, and the following discussion and conclusion we'll talk about later. And all vector of the word vectors rows are normalized to unit length, which is the L2 normalization, so that the cosine similarity and the dot product are equivalent after the normalizations. And vector normalization is applicable for all 4 methods, and it's applied in all the results.
All right, so before we get into the results, we'll cover the experimental setup. And so the hyperparameters that we just covered are shown in the table to the left, giving the explored values for each and the applicable methods. All models were trained on English Wikipedia, pre-processed by removing non-textual elements, sentence splitting, and tokenization. And each word representation was evaluated on 8 data sets, 6 of them being similarity, 2 of them being analogy tasks. And there were a total of 672 models in this experiment. And so getting into the results, this first table that we're going to be going over is showing the comparison between the hyperparameters in each of the 4 algorithms that we discussed. Specifically for this table, we're using a combination where the window size is 2 and it's not dynamic. We're taking no negative subsampling, no context distribution smoothing with alpha equal to 1, only using the word embedding without the context embedding, and we're using the default eigenvalue weights with P equals to 0. And for the analogy score, we're showing the 3-cos mole score, which is one of the analogy tasks that I've mentioned previously in the experimental setup. As you can see, it's a combination of different cosine similarities between the words in the analogy. And here's another table just showing a different combination of hyperparameter tuning and the performances from it. And then here's another table, more specifically utilizing the best combination of hyperparameters for each of the algorithms. And so the main result from this is that, that the results shown from the test results and the training results is that the improvements that can be made from hyperparameter tuning are feasible. And this was done through an Oracle experiment where the hyperparameters were first tuned on the test data, essentially providing an upper bound on what the potential performance could be from this hyperparameter tuning on the algorithms. And then when we compared when the test results were compared to the training results, this is what indicated the feasibility of this performance improvement. And additionally, another takeaway was that no single method consistently performed better than the rest, and we'll touch on this a little bit later in the presentation. Another thing that we wanted to take away from this paper is that hyperparameters can actually improve when we have a larger text corpus. One negative, though, is that training word vectors from a larger corpus might also be more costly in computation time. And so comparison that's also made in this paper is that we compare the SGNS algorithm and the GLOVE algorithm using a large corpus of 10.5 billion words, which is 7.7 times larger than the original corpus. And then on a side note, those are denoted with an LS at the end of the method in the tables. And it was found that SGNS actually scales nicely and GLOVE does not. And the table that I mentioned is observed here. It's also worth noting that the performance for each of these methods was done using twofold cross-validation for the hyperparameter tuning.
Okay, let's discuss what we can learn from the paper. Evaluating prior claims. So the first are embeddings superior to count-based distributional methods. It is commonly believed that modern prediction-based embeddings perform better than traditional count-based methods. However, this does not seem to be a consistent, significant advantage to one approach over the other. Therefore, the claim should be false. Second, is GLOVE superior to SGNS? The other paper, researchers showed a variety of experiments in which GLOVE outperforms SGNS. However, in this paper, SGNS outperforms GLOVE in every task. Only in some cases that GLOVE show a small advantage over SGNS. Therefore, the claim should also be false. Third, is PPMI on par with SGNS on analogy tests? In the other research paper, the results show that PPMI and SGNS perform similarly on both Google's and MSR analogy tests. However, the results in this paper show a clear advantage to SGNS, while the gap on Google's analogies is not very large. SGNS consistently outperforms PPMI by a large margin on the MSR dataset. The author conjectures that capturing syntactic relations may rely on certain types of context, such as determiners and function words, which SGNS might be better at capturing. Therefore, this claim is false as well.
This table shows all the performance difference of hyperparameter settings they mentioned in the study. And by looking at the table, we can see that it is generally advisable to tune all the hyperparameters due to its potential performance boost. However, they may be computationally expensive. So this leads to the recommended setting for the word embedding system in this study. So the first one would be since it's always supply context distribution smoothing to modify PMI, since it consistently improves performance on all the method it applies on, and is applicable for all the methods but GLOVE. Second, always apply eigenvalue weighting on SVD. Despite it is typically advised to set eigenvalue to 1 in a normal SVD setting, this study suggests that eigenvalue weighting provides a better performance. Third, PPMI and SVD's preference towards shorter context window, and in this case, it's window size of 2 in these experiments. Then SGNS always prefers many negative samples. And then we have SGNS and GLOVE should always be tuned with the adding context vectors variant. It is worthwhile to experiment with the variant since it's cheap to apply and it can result in substantial gains. Lastly, the paper suggests that SGNS is the robust baseline of all 4 methods. SGNS might not be the best method for every task, but it doesn't underperform in any scenario. Plus, it is the fastest to train and the cheapest in terms of disk space and memory consumption. Finally, we have the conclusion. Hyperparameter can have a large impact on the success of word representation methods, and it can apply very effectively on both traditional count-based and more modern neural network inspired based word embedding methods. And secondly, the paper and the author suggest that extend the concept of variable from just the task, data, and methods to the hyperparameter settings, since the papers clearly shows the benefits of having hyperparameter tunings. And this is the end of our presentation. Thank you for listening.
Thank you.
Thank you.